Okay, welcome everybody to this session. And I was arranging some change in the schedule. So the first presenter now will be Fellipe Sola. So let's start. Thanks.
Okay, can you see my screen?
Yes, now we can see your presentation.
Okay.
The idea, Felipe, is you present, and then you got a short time slot for question and answers. Okay, the idea is
Okay.
15 minutes presentation and 5 minutes question and answer.
Okay. So it's a pleasure to be here with you today. I will present my work about a book bias 1 volt, 5 gigahertz low power LC VCO with transconductance stabilization. And this work was made by me with support of Dr. Hugo Hernandez and my professor Wilhelmus. Okay, I'm a master degree student at University of São Paulo in Brazil. So this is the outline. First talking about the motivation. Then we talk about very quickly about VCO overview. Then the proposed topology, results, and conclusions and next steps. The motivations. Our research group has been working with low power circuits. So it's a very important feature for applications where the battery life is important. For example, Internet of Things, healthcare device, security, wearable devices. We don't want to recharge these devices every 8 hours. So we have been focused in those circuits. Along with that, we are focused in some RF circuits. So we aim in this Bluetooth low energy, which is a feature of the Bluetooth, focused on low power devices with lower cost and lower complexity. And in my case, I have been working a lot with voltage control oscillators. So we want to design something fully integrated with low power and with a good performance. Okay, and we have a challenge here in almost every RF circuit. But for example, in oscillators, when we reduce the power consumption, we increase the noise. So the performance of the VCO affects not only the VCO, but it affects the transmitter and receiver chain. So we have to take care with the low power reduction. Okay. A quick overview of the VCO. So this is a LC VCO. LC it's because we have a inductor and capacitor tank. So this topology uses a current reuse topology, which is a good topology for power reduction. This circuit has a minimum condition to start to oscillate and maintain the oscillation during its operation. We need to ensure that our transconductance of the NMOS transistors is equal to the transconductance of the PMOS transistors, and it's equal to 1 over RP. Okay, where this RP is the parasitic resistance of the tank. Okay, we also can calculate the oscillation frequency, but it's a very low formula for this type of circuit. I will just skip this. And I want to focus in this information because this topology here has a current source to bias the circuit. Okay, and this current source will ensure the right operation of the circuit. Okay, it's a very quick overview. The proposed topology, as we want something low power, so we will start to using the current rails topology. Okay, as we talked about in the last slide. Also to reduce the power, we reduce the voltage supply to 1 volt. This reduction in voltage supply will reduce both static and dynamic power dissipation. Okay, but now we have a problem with the circuit because due to this voltage supply reduction, it's more difficult to maintain 3 transistors in series biased in the saturation region. Okay, so we have to remove the current source here. Okay, and because of that, the circuit now is more sensitive to process voltage and temperature variations. Okay, and it's not good because we just want to design a circuit, plug in the system, and don't care if you are working at room temperature or at minus 20 degrees Celsius. We just want it to work properly. Okay. The proposed solution that we'll talk about in this work is to use adaptive bulk bias here on the transistors, the NMOS transistors of the oscillator core, to control the current consumption of the VCO and also achieve process and temperature immunity again. Okay, so this is the bias circuit proposed. This first part in blue is a low voltage beta multiplier. Okay, and we use this circuit to generate a current reference, which can be calculated with this formula here. But if we derive the transconductance of MB1 from this equation of the current, we see that we have now a constant GM, okay, and this GM is 1 over Rs, and it's a good thing because if you remember from the previous slides that we have a minimum condition that we need to ensure, and this condition is just fix the value of the GM of the transistors. So now you achieve this GM reference without any dependence of process, temperature, or voltage. So it's a good thing that you will use further. Okay. The second part here is a current mirror, and basically it's used to copy the IRF to this MC4 here. Okay, we talk about this MC4 later. Here we have a scaled replica of the on branch of the oscillator. Okay, this circuit is used to generate a VGS for MC4. Okay, it acts like a sensor to know where or what corner we are working or temperature, and the voltage here is applied to the gate of the MC4. Okay. Okay. The last part is a differential operation amplifier. Okay, and we use this amplifier to compare the voltage at VB and VA, and the output of this amplifier is connected to the book of NMOS transistors in the core oscillator and in the book of MC4. Okay, and how it works. So we have here a current mirror forcing a current here in the drain of MC4. Okay, but we also have a VGS coming from this part of the circuit, so it's kind of we have a conflict here because this VGS also defines the current of the drain of MC4. Okay, so this amplifier compares these nodes. Okay, and when VA is equal to VB, so the current in this branch is equal to this branch, and this output generates a voltage to the bulk of MC4 to control the threshold voltage of the MC4. So now we can have a VGS minus VTH of MC4, which will generate a current equals to we have. Okay. So now we have here in MC4 a current, which is a copy of the EF times a multiplicator factor defined by the size of this transistor here in the current mirror. Okay, and we also have the GM of MC4, which is a copy of the GMB Remember, it's a constant GM multiplied by the semi-factor. Okay. Just an important note here is you have to take care about the voltage of the bias, because it should not exceed 0.5 voltage, okay, in order to avoid current leakage through the bulk of MC4 and the bulk of the transistor, the NMOS transistors in the core of the oscillator. Okay, we can have a current leakage here greater than the current in the entire circuit. Okay, and we can do this just sizing the transistors of the current mirror. Okay. Now the final step is to size the NMOS transistors in the core of the oscillator. Okay, and we can do this. We should do this related to MC4, because remember we want to copy what we have here in this MC4, because we have a current constant GM here in MC4. So the multiplication factor can be calculated with this formula, and it's a function of the GM, which is constant, or GM reference, and the parasitic resistance of the tank. Okay. Once you have this multiplication factor, we just multiply the size of MC4 for this factor, and we have the size of our NMOS transistors in the core of the oscillator. This is the layout of the proposed topology. Okay, here we have the bias circuit, here the core of the oscillator, and here the huge inductor. Okay, the circuit was designed in the TSMC 108 nanometers. Okay, the total area of this layout is without the pads. Okay, here we have some buffer, but it's don't affect the size too much. Okay, the results. So all the simulation results here are performed using the layout structure with the Spectra RF tools. Okay, so on the left we have two plots comparing the proposed oscillator with other two topologies. Okay, and as you can see here, the proposed VCO has a barrier immunity for a range of temperatures. Okay, the GM variation is very better than the other oscillators here. And for power variation in the same range of temperatures, you can see it's almost constant. Okay, which is a good thing. It proves that we have a temperature immunity. Okay, on the right we have two plots of the Monte Carlo analysis. Okay, each plot has 3,000 samples with process and temperature variations. Okay, this first one here is the GM variation, and if you can see here, the proposed oscillator, most of the samples of the proposed oscillations is next to the mean value. Okay, and for the power, the same thing. Almost the most of the samples are here in the mean value. Okay, in the power we have this some samples here on the left due to the slow corner. Okay, but again it proves that we have a PVT immunity again. Okay, here on the left we have the frequency range that this VCO operates in a range of the for different corners. Okay, so we see that for the circuit operates right for any corner. Okay, we are inside the desired band. The output transient also proves that we maintain the right operation of the circuit in a range of temperature. Okay, so just to prove the PVT immunity. And the phase noise here, turns out this phase noise analysis is not correctly, because the phase noise simulation was adding some sideband noise into the desired signal. So it took me a time to realize the problem, but it's very simple to solve. we just select the desired sideband to be tested, and this is the correct one. So we have an improvement of 28 dBs in the phase noise. Okay. Conclusions and next steps. So again, this table is not correct. The phase noise value here. This one is correct. As you can see here in the table, we use this FOM to compare oscillators, and the lower the FOM, the better the oscillator. We have designed a circuit that has a FOM better than those proposed, but this one here, it's just because this one has a 20 times lower power dissipation. Okay, but it's discussed. It can be discussed later. The conclusion is that this work proposes VCO for low power applications using the TSMC 108 nanometers technology. Also use current rails topology with 1 voltage supply voltage, and a book bias scheme to control the GM of the NMOS at the core of the VCO. Okay, as you can see, the VCO meets the desired specifications, and also with the book bias technique applied, we also reach the right operation of the circuit for all process and temperature corners. Okay. The next steps now is to conclude the experimental tests that is delayed due to the COVID situation. We are facing some restrictions here in Brazil. And also I want to create a timing circuit for the bias circuit to have a better performance at slow corners. Okay, that's it. Thank you, and please let me know if you have any questions.
Sorry, was silent. Okay, thank you very much, Fellipe, for your presentation. Now it's time for question and answer. Question to Fellipe. Please, if possible, write a question in the question and answer section of the chat.
Okay. Just let me
Okay.
open.
Meanwhile, I can.
I think there is no one has questions.
Meanwhile, I got my question.
Okay.
What about linearity of the VCO itself? You know what I mean? Does this strategy affect linearity of the circuit?
What you mean about linearity? Because the oscillator is very non-linear circuit, because the
Yes, no, okay. Third harmonic distortion, for example, harmonic distortion, any kind of way you characterize a distortion.
Okay. It seems that this circuit don't have too much distortion. It's because due the LC tank, we just have a sinusoid wave at the output. It's kind of perfect sinusoid wave. I don't know if I answered your question.
Yeah, I think it'd be interesting to check. By linearity, I mean, you in principle are making the hypothesis that this is a linear oscillator. Okay.
Okay.
So in some way, you have to characterize distortion. I mean,
Okay.
in which
Yes.
terms it's an interesting parameter to characterize distortion, and if your strategy affects, improves, or is not does not affect the linearity of the distortion. I mean,
Okay.
you can characterize it in the way you're used to, but so it's okay. It's just an interesting thing to check.
Yes, of course. I will check this later. But I don't have any simulation or any information about this right now. Maybe I can have and send this information later.
Okay. Any other question? Yeah. Okay. Thank you very much.
Thank you.
Felipe.
See you.
So it's time for our next presenter.
Agora sim.
Okay.
Okay, can you hear me, Alfredo?
Yeah, I can hear you.
Nice.
So I think everybody is listening to us. So our next presenter is Samuel Marcin.
Yeah.
That's okay. And we'll present us a modeling and prototyping of a microfluidic device for DNA amplification. Your presentation will be in English.
Yes.
Okay, thanks.
Just let me check
Let's
how
start.
I share my presentation over here.
Yes, okay. You got a small screen on the
Okay.
bottom.
Mhm.
So you got 15 minutes, and then we got a small 5 minutes time slot for questions.
Great. So, are you guys seeing my presentation?
Yes,
Okay, great.
let's go.
So I am researching here at Unicinos, which is a university on the southern of Brazil, and I working at IoT chip, and mostly we work with MEMS and microfabrication sensors whatsoever. So my work is titled as modeling and prototyping of a microfluidic device for DNA amplification. So basically, just a background, DNA amplification is very useful tool for molecular biology, and nowadays it's being widely used for COVID testing, and it basically has three basically steps to perform that. The first one is named denaturing, where the strands of DNA are separated, and after that, there is a chemical compound named primers that binds with certain region of the DNA. And the last step is the extension step, where the strands are bind together. Each time the cycle is performed, the DNA content of this on certain